The High NA EUV machine, officially called the Twenscan EXE5200, is the largest and most complex lithography system ever built. It's a 180-ton machine that takes 6 Boeing 747s just to transport its core improvement, the lens. Built by Zeiss, the new 0.55 NA lens required developing a completely new mirror system. Remember, UV light is absorbed by almost everything, including glass, so traditional lenses won't work, and the difference between 0.33 and 0.55 NA, that's the difference between today's smartphones and tomorrow's AI supercomputers. So what exactly is this $400 million beast? Instead, the machine uses a series of ultra-flat multi-layer mirrors, each polished to an atomic level of precision. These mirrors must reflect EUV light without distortion while operating at blistering speeds. To give you a sense of scale, the smoothest mirror in this system has an unevenness less than 50 picometers. That's less than the diameter of a single hydrogen atom, but that's just the optics. The machine also requires a vacuum chamber that mimics outer space conditions, a tin droplet laser system that generates EUV light via plasma, and positioning systems that keep the wafer aligned to nanometer accuracy while it moves at several meters per second. The tiniest vibration can throw off the patterning, so has to be isolated from all outside forces, including Earth's natural seismic activity. Is more precise than a Swiss watch, faster than a bullet train, and more expensive than a fighter jet. Each High NA machine consists of over 100,000 parts sourced from more than 5,000 suppliers across the globe. Installing one can take up to a year, involving teams from ASML, Zeiss, and the customer working together in top-secret clean rooms. So why go through all this effort? Because without it, the next generation of 2 nanometers, 1.8 nanometers, and below chips simply cannot be built. And whoever controls this technology controls the future of computing. For $100 million, that's enough to buy a luxury skyscraper in Dubai or nearly 5 fully loaded F-35 fighter jets. So what exactly makes this machine so astronomically expensive? Let's break it down. 1. The precision optics by Zeiss. At the heart of the High NA system lies this mirrored lens system developed exclusively by Zeiss. These aren't ordinary mirrors, they are. For decades, lithography was dominated by Japanese players like Nikon and Canon. But ASML had a vision to push the boundaries of miniaturization through EUV, or extreme ultraviolet lithography. While the world doubted EUV's feasibility due to immense engineering hurdles, ASML doubled down, investing billions into R&D and forming strategic alliances with companies like Zeiss, the German optics firm. The gamble paid off. By the late 2010s, ASML had done what no other company could. They commercialized EUV lithography. Today, they hold a monopoly on EUV machines. And they're the only company on Earth building High NA EUV systems, a revolutionary upgrade that will define the next era of semiconductors. In 2024 alone, ASML's revenue crossed $25 billion, and each EUV machine it sells brings in $150 to $200 million. A High NA machines, they'll go for more than double of what makes lithography so critical. Why can't Intel or TSMC just build these machines themselves? To understand that, we need to break down how lithography actually works. At the heart of every chip is an insanely complex process called photolithography, a way to carve billions of tiny transistors onto a piece of silicon. To oversimplify, photolithography is like printing. A high-powered light is shined through a mask stencil that defines the intricate circuit patterns. This pattern is then projected onto a silicon wafer that's been coated with light-sensitive chemicals. Where the light hits, it chemically alters the surface, allowing ultra-precise etching. The more accurately and finely you can do this, the smaller the transistors get. And the smaller they get, the more you can fit onto a chip, making it faster, cheaper, and more power efficient. For decades, this process used deep ultraviolet DUV light. But as chip makers approached the limits of DUV around 10 nanometers, something had to change. That change came in the form of extreme ultraviolet EUV light, with a wavelength of just 13.5 nanometers, about 15 times smaller than visible light. This allowed for smaller, more precise patterns, helping the industry continue Moore's law. But there was still a catch. Even EUV machines have their limits. As transistor sizes reach below 2 nanometers, even EUV starts to struggle. Way forward, that's where numerical aperture, or NA, comes in. Numerical aperture is a key property of a lens system. It determines the resolution, how small a feature the machine can print. ASML's standard EUV machines use a 0.33 NA lens. But for the next generation of chips, this isn't enough. High NA EUV with a lens system rated at 0.55 NA. This jump might seem small, but in the world of nanometers, is monumental. High NA EUV allows chipmakers to print smaller features with greater fidelity, reducing the need for complicated and error-prone multiple patterning steps and the difference between 0.33 and 0.55 NA. That's the difference between today's smartphones and tomorrow's AI supercomputers. So what exactly is this $400 million beast? Polished to within 0.1 nanometers of flatness, made with over 40 alternating layers of molybdenum and silicon, and engineered to reflect 13.5 nanometers UV light with minimal distortion. Zeiss builds these lenses in a $1 billion custom factory in Germany, where the mirrors are so sensitive they must be crafted in gravity-neutral environments. The price tag for just the optical module well over $100 million to the UV light source. To even generate EUV light, ASML uses a CIF sounding system, a high-powered CO laser firing at 50,000 tin droplets per second, creating a plasma explosion that emits EUV radiation. This process happens at 10 times the temperature of the sun's surface, is completely contained in a vacuum chamber to prevent EUV absorption, and needs to operate 24/7 for months with nanosecond precision. Developing and perfecting this system alone took 2 decades and billions of euros. 3 vibration-free engineering. The machine's wafer and reticle stages move at several meters per second, but must remain aligned within a margin of plus or minus 0.25 nanometers. That's like aligning a rocket while it's moving at full speed, and making sure it stays locked on target. To achieve this, ASML uses active vibration cancellation systems, magnetically levitated stages, and real-time feedback control using lasers and sensors. Even Earth's own seismic activity had to be factored in. Facilities where these machines are installed often build special anti-vibration foundations for integration, customization, and logistics. Each machine must be customized to the customer's process node, infrastructure, and integration stack. It involves over 40 shipping containers, 6 to 8 Boeing 747s or equivalent air cargo flights, teams from multiple countries assembling it over the course of 9 to 12 months. On top of this, ASML includes service contracts, upgrade packages, and on-site engineers. The full life cycle of a High NA machine involves billions of dollars in total investment, and yet even with this massive cost, chipmakers are lining up to buy them, because when it comes to leading-edge chips, the High NA machine is the only